Good day, everybody. My name is Carl Beechler. I'm Lab Director at ALS Environmental here in Rochester, New York. I'm joined with my QA/QC manager, Vicki Collins. She's going to chime in, if need be, from time to time. I hope that what we're bringing to you will help you understand a bit more about the reports you get from labs and help you to understand the data on which you base your important environmental decisions. As you have questions, go ahead and type them in, and then at the end of the presentation, they'll be read aloud, and we will answer them for you. So, in this presentation, we want you to better understand how quality objectives impact the data and method choice. We want to explain to you the various quality control parameters that you see on a lab report. Some of the possible data qualifiers you'll see due to non-conformances. We're going to go over just the major ones. We really can't, we don't have time to go over all the potential qualifiers that you'll see. And ultimately, and most importantly, what the impact is on your data for these non-conformances. So most people, not everybody, but most people see the laboratory business as this mysterious box where samples go in and results come out. Nobody really knows what goes on. We're going to try to open that box up a little bit for you, let you peek inside, and you know, and really see what you're, and really see what we're doing, and you know, and how we get to the point where we're presenting you with those all important results. And you know, hopefully you will come out of this with a better understanding of what we're doing, which will allow you to better interpret the data. So how do you know if the results are good results if you get a report from us? You know, what are the data quality objectives? You know, laboratories in general don't say results are good or bad. We're just reporting the results as we find them. The usability of the data is based upon project data quality objectives and the accompanying QC measurements reported within the data. Laboratories must follow promulgated rules as set by the EPA and the states, and of course the methodologies as well. So when we're looking at quality control parameters, in general, this is a kind of a generalization, but there's 3 levels of QC. The method level, the batch level, and the sample level. There may be others that are method defined or project specific, but what we have here in terms of method quality control parameters is sensitivity and the linear range of the calibration. On a batch level, we have the method blank, we have laboratory, LCS stands for laboratory control sample, MS stands for matrix spike, MSD stands for matrix spike duplicate. You know, we can also have duplicate LCSs too, laboratory control samples. I'll go into that a little bit more later. And we also have duplicates of samples, just a plain old, you know, replicate analysis, duplicate analysis of a sample. On the sample level, we have surrogates. Again, we have matrix spike dupe, which, you know, helps on the sample level, and we have internal standards. So, focusing first on you know, method and sensitivity, there's really two points to be concerned about. You know, and I'll continually refer back to these during the presentation, but we have the method detection limit. It's a statistically derived limit based upon some guidance that's in 40 CFR. Statistically, it's different from a blank. Basically, it's a qualitative value, not a quantitative value. This isn't a value that it's not a value that we directly measure or can measure. It's really it's a statistical entity. Okay. However, the reporting limit is a real, you know, value, so to speak. The reporting limit, or MRL, method reporting limit as we sometimes call it, is the low point on the calibration curve. It's the lowest standard on the calibration curve. And I'll show you a little bit, I'll show you some examples of that here coming up too. And this is the point of where we can start determining accuracy and precision within the linear range of the sample, or I'm sorry, within the linear range of the calibration. Now the calibration has its own QC criteria. Generally we want to know if the resulting curve is linear. So a calibration curve plots known concentration versus instrument response. In this case we have absorbance as instrument response. Depending on the instrumentation, there may be something else there on the y-axis, but on the x-axis there's always concentration. But the linearity of the method determines the concentration range. So here we have, it looks like we have four standards essentially, and it looks like 2 is the lowest, so that would be where the MRL is, and the MDL is somewhere below 2. Okay, it's some value, some statistically derived value below 2, and 8 is the highest standard. And what our goal is not only to have a linear range to use to compare sample results to, but we also want to make sure that we're analyzing your samples in such a way, either straight or at dilution if need be, so that the resulting concentration is somewhere within that linear range, if there's a detection, obviously, between the low standard and the high standard. So when we're talking about the linear range, this is basically kind of like an expanded view. There's usually a concentration range in which the response makes a predictable line, or curve as we sometimes say. This is the range of concentration we use for calibration. You can see there the valid range. That's a valid range of the curve. The detector might become concentrations above this range may not fall in line with the calibration curve. It might be above in the E flag range, and we'll talk a little bit later about E flags, or in the J flag range. Now J flags, that's that area there below the lowest standard. You can see here on this graph we have a low standard of 0.01, and then we have a scattering of results there near the bottom. They're below that, but above the method detection limit. And we flag those J as estimated. Again, we'll talk about this a little bit more later. Responses below the linear range may be erratic, as it is here, or they might flatten out. The instrument response cannot be used to determine accurate concentration here at this point. So, the sweet spot here is the valid range. If we get a result of your analysis in the E flag range out of the linear range, then we'll dilute to get the result to within that valid range, to within that linear range. Now the QC that's associated with the calibration, we're looking at linearity and the ICV, or the initial calibration verification. The linearity is a limit on how much the points of the curve deviate from the expected or from a line. And RSD, that stands for relative standard deviation from the average RF, which is the response factor. The response factor is a proportion of the response to the concentration. It should be about the same from point to point. Calculating the RSD, or relative standard deviation of the response factor, shows how much the points vary from the expected. The lower RSD is better, and you might see this in the calibration section of your report. If the relative standard deviation is in limits, the average of the RFs is used in the calculation of sample concentrations. The relative standard deviation is generally used for organics. The correlation coefficient, however, is generally used for inorganics. Linear regression, where we're measuring how well the points fit into a line. We also have the ICV, or initial calibration verification. This is a different source than the standards that we use to create the calibration curve here at 2, 4, 6, and 8. This verifies the standard used for the initial calibration curve and it's performed immediately after the calibration. So we've done all this before we've even gotten to your samples. And there's more that we do too. We don't stop there. And this is really true of all labs. This isn't just ALS. So now we have to establish if we have a good calibration curve. How do you know if it's good, if it's still good after you've run a couple of samples? We have the continuing calibration verification, or the CCV, as I'll refer to it. This is performed at defined times to verify that the instrument is still producing the expected responses compared to the initial calibration. Initial calibrations, as you can see there, can be good for short duration or years, depending on the stability of the system. However, the CCV is expected to perform within the defined criteria. A CCV that exceeds the expected range indicates potential bias and requires recalibration and additional sample analyses. So again, this is all stuff we're doing before that has to pass muster before you even see the results. But now we're at the point now, as we go into batch quality control, where we're actually starting to run some samples. And we're looking really here at two analytical processes, or really two ideas that help us to determine, whether results are, have good quality control. We have the accuracy and the precision of the data. In terms of accuracy, we're looking at the laboratory control samples, which I'll talk about a little bit more later, and surrogates. These measure the closest of a measurement to the actual value. This is determined from control samples in each batch. Many of you have probably seen these bullseye representation, trying to differentiate, accuracy from precision and so forth. You can see the target there, if you can envision the holes as being results. On the left there, we have excellent accuracy and precision. We're right on the bullseye, and they're grouped nice and tight. However, on the right, we're fairly close to the bullseye, but the results are scattered all over the place. So precision is bad. On the upper right there, we have very precise, nice tight grouping. However, we're pretty far away from the bullseye, so we're not very accurate here. And in terms of precision, quality control parameters we use to determine the precision end of quality control is duplicates, and by duplicates I mean we're analyzing samples twice, or matrix spikes and duplicate matrix spikes, LCSS and duplicate matrix, and duplicate laboratory control samples, where we're taking those quality control parameters and doing them twice. And I'll show you a little bit later how that kind of kills two birds with one stone. So with precision, it measures the ability of an analytical method to reproduce its own measurement. In other words, bias. And that's done by measuring replicate samples, or by measuring replicate quality control parameters like matrix spikes or LCSs. So what should you expect from the lab? First thing you got to do is choose the methods based on your analytical needs. For example, take 1,4-dioxane analyses. The recovery in the full list of volatiles or semi-volatiles by GCMS methods is poor, but if you use SPE and SIM analyses on these, the accuracy and precision is much more reliable. So getting deeper here into batch quality control, the requirements are defined by the SOP and the method, and sometimes there's additional requirements in site-specific QAFs, but in general here, we have the method blank, we have the laboratory control sample, we have the matrix spike, and very often we have duplicates of the matrix spike in the LCS. And again, like I said before, there might be others that are method defined or specific to the project. So let's look at method blanks first. The purpose of a method blank is to check for possible analyte contamination in the system. The procedure that we use is we take a aliquot of reagent water or other analyte free matrix like, say, sand that's clean. For solids, it's prepared and carried through the entire sample preparation and analysis procedure from beginning to end. And as we're looking at the information, it'll demonstrate that the analytical system itself does not introduce contamination into the analysis. It demonstrates that any positive sample results are not false positives. And in general, we report the method blank to the method reporting line unless there's a specific request to report to the MDL. So what's the impact on the data here? The method blank is very, very important criteria. As you can see here, we have a snapshot of an analytical report where we're doing some semi-volatile analysis. And you look there and you say, oh wow, we have a hit of phenanthrene. This J flag, remember before we were talking about results between the method detection limit and the method reporting limit. The method detection limit being a calculated result, a qualitative result, and the MRL, which is actually the low point on the standard curve, which we're actually analyzing an actual standard. So that's a known result. So we have 0.07, which is between the MRL and the MDL. So we J flag that as an estimate. That's an estimated result. If the target analytes are detected at the method blank, or excuse me, if the target analytes are detected in the method blank above the reporting limit, detections in the samples might be due to laboratory contamination. If the analytes are detected in the method blank but not in the sample, the data is not impacted. So let's look a little deeper here. Here's on the same run. Here we have an actual analysis of one of the samples in that batch here. So now look at phenanthrene here. We got 2.96. Now the convention used in laboratories is the 10 times rule. If the concentration of a sample analyte is greater than 10 times the concentration of the method blank, the effect of any potential contamination is judged to be non-significant from a laboratory perspective. So going back here, you can see 0.07. I mean, that's orders of magnitude less than the actual phenanthrene result in the sample. So we determined that that there's no effect on the sample itself. So we go ahead and we release the data. If it's less than 10 times, then the data is reported with a, in this laboratory we use a B flag, and that will indicate that that there is a potential that there is a contamination issue. All right, let's jump into LCSS, or laboratory control samples. Fairly straightforward concept here. The purpose is basically to document the performance, our performance. We take an aliquot analyte free matrix, deionized water, for example, and then we spike it with a known concentration of the target compounds. Now, this is not the same standard that we use for the calibration curve. It's completely different. With a known concentration of the target compounds, and this is carried through the entire sample preparation and analysis procedure as part of the analytical batch, just like the method blank. From beginning to end, it follows right along with the samples. When we're evaluating, the recovered concentrations are compared to the true spiking concentrations and evaluated against predetermined acceptance criteria. So here we have another snapshot of a report here. And now, interesting here, we have the laboratory control sample result, and now we also have a duplicate laboratory control sample result. We'll go into that a little bit more later, the duplicate part of it, but what the impact on the data is for the recoveries. If the recoveries are above the acceptance limits, it indicates the potential for a high bias with analytical results, and below the acceptance limits, it indicates the potential for a low bias in the analytical results. If the LCS recovery is above acceptance limits, but the target analyte is not detected in the sample, the data is not impacted. However, on the other side, let's say for example that we have a low recovery of pyridine. It's out of range on the laboratory control sample, And, but the sample analysis shows a non-detect for a pyridine. Now that's a red flag. We have to go back and start all over again, because that indicates that low bias on the LCS might be an indication of something going wrong with the method that's creating a situation where we're not recovering all of the pyridine. Now surrogates. Let's jump into surrogates. Surrogates are very interesting, very useful. What we're trying to do is with surrogates is to identify chemical or physical interferences in the matrix itself. So we're actually taking this is specific to organics, but we're taking an amount of sample, and we're actually spiking them with compounds that are not normally found in the environment but have a similar chemical composition and behavior. The surrogate compounds are presumed to not be present in the collected samples, and they're added at the time of preparation and analysis. This is included for quality assurance purposes only. Okay, so let's take a look at some surrogates here. We have this is for a run of semi-volatiles here. And we have some compounds here like 2,4,5-tribromophenols and 2,4-biphenyl and 2,4-phenol. Compounds they're just not found in the environment. They're not in common target lists. So, but they're very similar to some targets. So they're terrific to use as surrogates. Now, however, take phenol for example. Now, phenol is a common analyte, but we get a surrogate standard that's deuterated. Makes it a little heavy, but it's still phenol. So again, it's a very useful tool here to try to find something very close to what the target contaminants are. Now, when we're evaluating, the recovered surrogate concentrations are compared to the true spiking concentrations and evaluated against predetermined acceptance criteria. You can see here we have good recoveries here. So what's the impact on the data? Recoveries above acceptance limits indicate that there could potentially be a high bias with the analytical results, and recoveries below acceptance limits indicate that there could potentially be a low bias with the analytical results. Now, these nonconformities related to surrogate recoveries are the result of chemical or physical interferences present in the sample. Your laboratory might not be able to eliminate the bias. The lab will often attempt to eliminate the interferences by doing additional cleanups if allowed by the method or by dilution. Okay, now matrix spike 2. This is a very important quality control procedure, and I think it's my favorite, and I'll tell you why. The purpose is to identify the chemical or physical properties inherent in a sample matrix. So what we're doing here, this is kind of like a surrogate. However, we can do this for virtually any analyte that we do here, whether it's or any laboratory. On the inorganic or organic side, we're actually taking your sample and we're spiking with a known amount of the target contaminants. Okay. How we evaluate this, the recovered concentrations are compared to the true spiking concentrations and evaluated again against predetermined acceptance criteria. Here we see some inorganics here. We see some good recoveries. So this is a very useful tool. What's it telling us here? Recoveries above the acceptance limits indicate an interference that could potentially result in a high bias with analytical results. Recoveries below acceptance limits indicate an interference that could potentially result in a low bias. This is telling you a lot. If you're getting a low bias or high bias on your analytical results, if you're out of range here and all other quality control parameters are good, like the method blank and the LCSS and everything else, and the calibration criteria, there's something going on in your sample. It's really, I feel really the best way to determine if there's any interferences in your sample, because that's really one of the biggest obstacles you have to reporting true defensible data is, whether there is, an interference or not. Now, because nonconformances are related to spike recoveries, as a result of chemical or physical interferences that are present in the sample, these interferences must be identified and removed to obtain acceptable spike recoveries. In some instances, this might not be possible, but it's telling you a lot. Here's an example. Let's say you're analyzing your sample for hexavalent chromium, okay? And then it comes back, the spike, very, very little to no recovery. What's very likely happening there is there's a reducing agent in the sample that is reducing the hexavalent chromium to trivalent chromium. So it's not a failure of the analysis. Matrix spike is doing its job. It's telling you that there's something there that is creating a low bias in your analytical results. And this is a very good tool for the user to know that something is going on with the sample. Whatever laboratories that you all are using, I would recommend very highly, very useful tool. If you're not asking your laboratory to take one of your samples and if you're not specifying a matrix spike on it, you should really do it. Very, very good tool. So useful. Really gives you a lot of peace of mind, I think, which is why it's my favorite quality control criteria. Right, Vicky? It is. It's great. So, all right, enough on the matrix spikes. Let's talk about relative percent difference. Of course, we're using this to evaluate the precision of the analysis, how tight that grouping is. If you remember, going back to those targets, the nice tight grouping with good precision. What the purpose is to evaluate the reproducibility associated with a sample analysis. What you see here is the procedure that is the calculation that we use to determine the relative percent difference between a sample result and then a duplicate or a matrix spike, and a matrix spike duplicate, or an LCS or an LCS duplicate. It's a calculation we use to evaluate. So let's see what we have here. When we're evaluating, we're taking a look at the calculated relative percent difference and evaluating it again against predetermined acceptance criteria. So we have a couple different representations here. We have acid-soluble sulfide. You can see a sample result there of 4.6. The duplicate is 4.5. Great RPD limit of 20, and we got an RPD of very, very good, very excellent precision on this. Let's take a look below here at at these herbicides here. Here we've killed two birds with one stone. This is great. We have the LCS here determining accuracy. Very, very good recoveries here, and then we did a duplicate of the laboratory control sample here. So now we've introduced a determination of precision too. As you can see, all the control criteria are very, very good. And of course, like I mentioned before, you can do this on the matrix spike side too, in MS and MSD. Very, very good tools for you to evaluate your data. So anyway, what's the impact on the data? The relative percent differences above the acceptance limit indicates a potential matrix effect, such as sample non-homogeneity, which may be affecting the ability to reproduce analytical results. These nonconformances are often related to relative percent differences are more often than not the result of interferences present in the sample. By interferences, it's usually a situation where you have non-homogeneity in the sample. For example, like a wastewater treatment plant is a good example, where you have a sample where there's a lot of solids that might be floating or suspended or settlable. Very, very difficult, and although we have great procedures here, as all labs do, to homogenize the samples. If you're pouring out 2 aliquots of the sample, it's very difficult to get a completely accurate representation of those solids out of the 2 pores. So once everything is said and done, you know, there are situations that will arise where there's non-conformancies, things don't go as planned. Each analytical SOP, you know, that we have details procedures to deal with these non-conforming events where QC has failed or whatever. When this happens, the analysts and managers, you know, involve project managers at laboratories who then communicate with the client to determine a plan of action, whether their results are reportable or not, whether we need to go back and do some reanalyses. There's always documentation of non-conformances so that we can, you know, basically not repeat it again. Here's some of the qualifiers I was talking to you about. As you can see, there's quite a few of them. You know, this is these are the ones that we use. And you know, and it's similar to ones that other labs use. You can see here the E flag. The concentration has exceeded the calibration range of the specific analysis. That's results that are, you know, above the linear range of the calibration curve. So this is good information here. And if there's something on here, you know, if you see a flag on a report and you go to the key and you don't understand, I would encourage you to call your laboratory so you can really fully understand what impact this flagging has on your samples. Because I mean this is really what it's all about. You want to make sure you understand the data, and laboratories want you to understand the data so that it's of most use to you and to your clients if that's the case. That's pretty much all I have. I'm hoping maybe some good questions came up that I can answer, or possibly Vicki can answer.